Hello, and welcome to Ian and Cole's Problem 83. A uniform solid cylinder with mass m and radius 2r rests on a horizontal tabletop. A string is attached by a yoke to a frictionless axle through the center of the cylinder, so that the cylinder can rotate about the axle. The string runs over a disc-shaped pulley with mass m and radius r that is mounted on a frictionless axle through its center. A block of mass m is suspended from the free end of the string. The string doesn't slip over the pulley surface, and the cylinder rolls without slipping on the tabletop. Find the magnitude of the acceleration of the block after the system is released from rest.
As any good physicist knows, you should make a force diagram first. Miss Mills, are we good physicists? 'Cause we made one too!
You can see all the forces clearly labeled below, but please pay special attention to our tension forces as they are the most important for this problem. We have given them distinct labels to use later on. There is the horizontal tension, which we have labeled tension 111.55, and the vertical tension, which we have labeled tension 3.1416.
We summed the forces on the block and isolated T 3.1416 to be mg minus ma. What we did next is something called pure rotation, which Miss Mills talked about a while back. Picture that the cylinder is stationary and rotating around an axis at the point of contact between the cylinder and the table. With this approach, we found the moment of inertia of the cylinder based on the new axes by using the equation for I parallel. This new moment of inertia ended up being 6 mr squared. We then summed the torque of the cylinder using tension 111.55 and the calculated moment of inertia. We substituted A tan over R for alpha. We then calculated tension 111.55 to equal 3/2 ma.
Our next step was to sum torque for the pulley, and we ended up calculating that 1/2 ma is equal to tension 3.1416 minus tension 111.55. Substituting in the previously found tension values allowed us to solve the equation for acceleration, which equaled g over 3, or on Earth, 3.27 meters per second squared.
As any good physicist knows, you should make a force diagram. No, I'm gonna keep this. We're keep going. And the force diagram is important because if you're a good physicist, I know we're not, but like, holy crap! Are you okay? Okay, we're keeping this.